Another very interesting and growing area of robotics is biomimicry. Now, biomimicry has been talked about as the conscious effort and conscious emulation of life's genius. So we see things in nature, and some of the things we see in nature just amaze us, they wow us, that they seem so well designed to perform a particular task. And engineers will often turn to things that we see in nature for inspiration of new ways of solving problems. Now, we call it biomimicry if there's conscious forethought, rather than we develop a robot and then we say, that looks a bit like this, but we didn't actually design that into it in the first place. It's where we actually think about these things before we design it and design that into the product or design. And typically it's not just straight copying. We're not actually trying to create an animal through some sort of biological engineering process. We're trying to emulate some of the properties of that animal, or take some of the concepts and use those concepts to improve our designs or create a new design in some way. Now, robotics is one of the engineering areas to really employ biomimicry, but there's others as well. One common example that's cited is Velcro. Velcro came about, there was an explorer that went exploring one day and found that these burrs were getting embedded in hair and his dog's fur and things really easily, and they were very difficult to take out. When he looked under them at the microscope, he saw all these systems of little hooks in there, and he tried to create a system to do that synthetically. And he filed the first patent of Velcro, and it's something that we see all the time, all over the place. So one of the robots that we see that employs biomimicry in a really obvious way is one called StickyBot. So gecko feet have millions of hair-like little structures that allow it to cling to various objects and walk straight up walls, for example, or even on glass. They use van der Waals forces. At Stanford, they've created a robot that uses special pads on the feet and the way the feet are actuated on the wall to do a similar sort of thing. So they've called it StickyBot, but that's not the only application for it. They've talked about applications of using micro-aerial vehicles. So think about a little drone that you might want to stick to the side of a wall or stick to a roof or something like that. Rather than using a pneumatic system that uses lots of energy to try and create a vacuum seal and things like that, you could fly it up there and just stick it on the wall and use virtually no energy in the process. Another application that we've seen is in sonar. Bats and dolphins use sonar or echolocation to work out the distance to objects, whether it be an obstacle or whether it be food, something that they're trying to track. This is now something we commonly use for submarines. We see it in fish finders, but we see it in robot-based sensors as well, where we can work out where obstacles are and avoid those obstacles based on the sound that's reflected back off them. Here's another one. Very fancy robotic trunk that Festo have developed, modelled on an elephant's trunk. Basically, an elephant's trunk is a few things. One is very, very strong, but it's very, very dexterous as well and has lots of different positions that it can move in. So they've developed this robot trunk along a similar line of what an elephant's trunk looks like, at least on the outside. Robot arms are another area as well. We talked before about the Stanford arm, but think about this. We call them anthropomorphic arms, basically because they take on some properties of humans and their copies. They're great examples of biomimicry. Here we even label the joints as a shoulder joint and an elbow joint and a wrist joint and an end effector, just like what we actually have ourselves. Vision systems are another area, including the basic vision systems and the concepts of having lenses, for example, and an iris that we can increase and decrease the aperture based on lighting levels. Those things have been around for many years now. But newer innovations like moth eyes that are being used to create high-resolution telescopes and have very great low-light performance, and fish eyes that have series of parabolic mirrors and hemispherical domes in them to really improve low-light performance and take images in something that pretty much looks like complete darkness to us. Fish employ these because they're swimming around in very murky and turbid water, and it's very difficult to see what's going on. Another one, a starfish gripper. Soft robotics is an interesting area, and Harvard University is moving into this area. They've modelled starfish and looked at how starfish can sit and grab on to very irregularly shaped rocks and things like that. They've used silicon rubber and pneumatic channels that run through here to grab awkward and delicate objects. Here we see it picking up a non-boiled egg, so a very soft egg that they need to be very careful of, and it does so quite well. And so we see a number of concepts inside biomimicry, and the list keeps on growing and growing and growing outside of robotics as well, where we see things that are well designed from nature, and we emulate some of those concepts and improve our own designs or create new designs that solve particular problems that we have.